We're going to look at the binomial theorem. It is a shortcut way to expand a linear factor that's multiplied by itself more than 2 or 3 times. So the binomial theorem works for an expression called a binomial. In principle, it's easy to raise a plus b to any power, but the higher the power gets, as n gets higher and higher, the expansion gets more and more difficult to do by hand. So this is a shortcut way to expand a binomial raised to a higher power. So we're going to look for a pattern, and we'll see that a pattern does arise. If we raise a plus b, the binomial, to a power of 1, well, that's easy. Raising it to a power of 2 is just that FOIL, first outside, inside last, or rainbow method, as it's called as well. But the higher that we get in our number n, the higher power, it gets a little more difficult to do analytically. So we're going to take a look at this last one here, this a plus b quantity raised to the power of 5, and see if we see some sort of pattern that comes along. And we absolutely do. If we look at the powers on a, the very first term in the binomial, and a can be anything. It can be a real number, it can be a variable, it can be a variable with a coefficient. A is just a placeholder for whatever is here in front of this plus sign. And so the power of a in each term descends by 1. It is the same as n, so we would call this n. Here's n minus 1, n minus 2, n minus 3, and so forth. And then let's look at the exponents on b. And for each term that b is in, the power on b increases, starting at 1 and goes all the way up to n. So with the observations, we can use this not just on the number 5, but we can use this on the number n. So we can, no matter what n is, we can very easily come up with the exponents on a and b, or the first term in our binomial and the second term in our binomial. Those are very easy to come up with. What gets a little bit more involved is how we come up with those numerical coefficients that go along with the number n. So we're going to have to determine those coefficients, and the binomial coefficients involve factorials. Factorials are a shorthand way of writing subsequent or consecutive numbers that are multiplied by one another. So in factorial, we start with 1, then times 2, then times 3, and we multiply every single integer from 1 all the way up to n. We multiply those together, and we say that that is n factorial. So for instance, 6 factorial is 1 times 2 times 3 times 4 times 5 times 6. We'll also just very quickly define 0 factorial as having a value of 1. There's a lot of mathematics right there involved in this equal sign, and we're not going to explore those mathematics right now. I just need you, for the purposes of the binomial theorem, to take this on faith that mathematically this was proven to be a true statement. It is true that 0 factorial does indeed equal 1. So we know now how to expand n factorial, and we know that if we ever encounter 0 factorial, that is equivalent to 1. And so we'll just substitute 0 factorial with 1. Now here is the formula for coming up with those coefficients in our binomial theorem. And let's figure out what n means. Let's figure out what r means. So n and r are non-negative integers. N can be 0, r can be 0. That's why it's non-negative. Otherwise it would say positive integers. So n and r are either 0 or some positive integer. And the coefficient is denoted by this little operator notation here. It's an open parentheses with n over r. There's no line or anything in it. It's not a fraction. It's just notation. Anytime you see this, we know that we are dealing with this formula, and that is n. This n and this n are the same n. This r and this r are the same r. So we know that it's n factorial over r factorial times the difference between n and r, n minus r, quantity factorial. And it turns out that no matter what n is and no matter what r is, we can actually find the coefficients of any binomial depending on n. So here, let's just practice on the coefficient. If we have n equal 9 and r equal 4, then we just plug it into the pieces of this formula for our binomial coefficients, and we find 9 factorial over 4 factorial times 9 minus 4, or 5 factorial. Now this is every number multiplied together from 1 up to 9. Excuse me, every number from 1 up to 4 and every number from 1 up to 5. So let's just write those out, and we'll see very quickly that a lot of things cancel. 9 factorial contains 5 factorial. So let's just get rid of 5 factorial top and bottom because that has a value of 1. So actually what we have here is 6 times 7 times 8 times 9 divided by 1 times 2 times 3 times 4. We could also, although we won't here, we could also simplify things. 8 divided by 4 is 2, 9 divided by 3 is 3, 6 divided by 2 is 3. So we could, even though it looks like it'd be terribly difficult to find these values by hand, they're really not that difficult. We could easily even simplify this more and come up with a easy way to find the values of something factorial over another factorial. So here's another one where n equals 100 and r equals 3. We just substitute that into our formula for the coefficient and we simplify things. It's very easy to simplify because 100 factorial contains 97 factorial. So again, it's not that difficult to actually come up with these coefficient values at all. Just keep in mind that you're going to have common factors top and bottom that are going to cancel quite nicely. So it may seem a little difficult. You don't have to actually get your calculator and plug in 100 factorial. As a matter of fact, your calculator is not going to like that very much because that's an enormous number. So remember that we're going to do this just old-fashioned. We're going to write it and we're going to realize that we're going to have common products that are going to cancel top and bottom. So here is the binomial theorem where these coefficients, these values right here, are defined by this formula. So if we are adding a plus b raised to a power of n, then n is the top number in all of those coefficients. R starts at 0 and iterates up through the positive integers all the way up to n. So let's practice one in particular. Here is the binomial theorem, the expansion for the quantity x plus y to the fourth. Now we did a plus b. A can be x and b can be y. It's not going to be a problem. So the binomial theorem expansion says that whatever is in the first place here, those powers started in and they reduce by 1 for every term there is in there. So 4, 3, 2, 1. And then the other term, they ascend, they increase 1, 2, 3, 4. So all we have to worry about once we realize we can get the x's and the y's very quickly is we're going to have to plug these values into this formula and come up with the coefficients. So 4 over 0, the binomial expansion for that is 4 factorial over 0 factorial times 4 minus 0 factorial. So that's 4 factorial over 4 factorial. That's very straightforward and easy. That's just a value of 1. For 4 over 1, we get 4 factorial over 3 factorial. So that's 3 factorial times 4 over 3 factorial. Your 3 factorials cancel. And so we continue on with this, increasing our value of r starting at 0 and stopping at 4. So there are all of our coefficients, 1, 4, 6, 4, and 1 right there. And so it's very easy. We would still be working on, multiplying x plus y times x plus y squared. So it gets rid of, even though this looks a little clunky, this is brilliant compared to what we would have to do even doing this to a power of 4 by hand, gathering like terms, adding all those coefficients, all that kind of stuff. So make sure that you have that formula written down. Make sure you understand the role that r plays and how you handle r, how you handle your powers, and what you do with the number n. So come to class next time and we'll practice the binomial theorem.